Hello, everyone. Sorry for the delay. Well, there has to be an introduction, so I'm happy to come back. Welcome everybody to our next installment of our Colloquium series. It's a great pleasure to have Christos Papoutsellis, a compatriot of mine from Greece. But after doing his PhD in Greece, spent great amount of time in France as a postdoc, and now he's a research scientist at UCSD. And today he's going to talk about high-order modeling of long dispersive waterways. Please, Christos. Hello. Thank you very much for the introduction and the invitation and the opportunity to present one of the topics I'm working on. So I will introduce. I will be talking about surface waves today. So water waves in the ocean that are driven by gravity, and they propagate on the surface of a fluid, which for our purposes would be the ocean. I will introduce the problem and the mathematical equations that describe this wave propagation problem. I will make some remarks about what is known, the state-of-the-art model that we use today, and then I will introduce a modeling approach using variational methods to derive model equations. I will discuss and compare in an analytical level with other existing classical and recent asymptotic models, and I will close with some numerical examples. Let me start with some figures of water waves and something that you can find in Feynman's book, lecture on physics. And the point here is to highlight that surface waves can do a lot of stuff and are very complicated, and they have very rich nonlinear dynamics. For example, here you can see something that we call cross seas. So that happens usually when you have two weather systems that send waves from different directions, and it's considered a hazard. Here you have, interacting solitary waves in very shallow water. This is from the Japan tsunami, something that happened, in a canal, let's say. And this is a deeper sea, let's say, with, you can even have turbulent dynamics. So the physical assumptions is that we're going to assume that our fluid is ideal and homogeneous, so density is constant, no viscosity, it's incompressible, the flow is irrotational, so we neglect vorticity. Our free surface eta is the surface elevation, let's say. So we assume that our free surface is always a function, so we don't have overturns and stuff like that. The free surface is impermeable, means that if you have, a fluid particle initially on the surface, it will remain always on the surface, and the bottom surface is impermeable as well. So you don't have transport between these two surfaces. The first assumption gives us this equation, which is called also Bernoulli equation. Phi is the velocity potential, which has to satisfy also the Laplace equation in the entire fluid domain. The velocity of the fluid is given by the gradient of the velocity potential classically, and the free surface condition is written in this way. So the time derivative of the free surface elevation has to be equal to the normal derivative of the fluid on the free surface, and the bottom surface impermeability condition is written like that. It's a Neumann condition, let's say, evaluated on the bottom. These are the main equations of the problem. The difficult thing with them is that the domain is unknown. It evolves with time, so it belongs to the class of free boundary problems. Because eta, okay, here you see it fixed in the picture, but it's something, it moves. So the shape of the domain is part of the unknown of the problem. There is a variational principle for this problem that says that if you take this functional, which from Bernoulli's principle, we can say that it is the pressure, which is somewhat unusual for variational principles, but this is something unique in the problem. So if you take this functional and you compute the variational derivatives with respect to eta and phi, you get all these equations. This is one important result. And the second important result is that you can reformulate this problem as a Hamiltonian system. And this was done by Zakharov in 1968 and further elaborated by Craig and Sulem in 1993. And the main ideas here is that we can introduce psi, which is the trace of the velocity potential on the free surface, evaluated on the free surface. And then Zakharov remarked that if we have eta and psi, then we can write down this boundary value problem for the Laplace equation, which is solvable. So if you have eta and psi, phi is uniquely determined, and you can uniquely define this quantity, the normal derivative, which is called dTn, which is actually the Dirichlet to Neumann problem. That means that you give the Dirichlet data and you calculate the Neumann data. So you can write it like that. Now, the good thing with this is that it gives you an idea how to solve the problem numerically, which is not very evident here since the domain is moving. The difficult part, if you want to solve this numerically, is that along the evolution, you always have to solve an elliptic boundary value problem in the entire domain. Non-local here means that this system of PDEs doesn't contain only usual differential operators. It also contains the Dirichlet to Neumann operator, which is non-local in the sense that in order to compute it in one location in space, you need the entire information from eta and psi, and you have to solve a boundary value problem as well. So this is a non-locality, which is a classical feature of fluid mechanics. Here is how it is expressed through this free boundary problem. So there are two basic things happening in water waves. You have dispersion. This is, a very old result from Cauchy and Airy. So if you linearize the problem and you assume that you have plane wave solutions, in order for this problem to be solvable, you get this relation that we call the dispersion relation. It's actually a very important relation because it relates, if you want, the frequency omega with the wave number. So it connects the temporal and spatial scales of the problem. And what it says is that different wave numbers or different frequencies travel with different speeds, what you see here in this animation. The other important thing is that water waves are also nonlinear. So, for example, Stokes in 1847 solved the problem at second order, if you want, and deduced that the frequency of propagation also depends on the wave height. That is to say that larger waves travel faster, something that you don't have in the linear regime, let's say. And of course, when we model the problem, so when we replace the primitive equations, if you want, the original equations with something simpler, we want to preserve these characteristics as much as we can. So about long waves, long waves. So in finite depth, when the depth is finite, here is our domain, we can introduce three typical lengths. This is H0, which is the characteristic depth of the fluid, if you want. Alpha, which is the characteristic amplitude of the waves that travel. And L, which is the characteristic wavelength. From them, we can introduce two dimensionless parameters. The nonlinearity, which is the ratio of alpha over H0, and what we call soundness, which is the most important parameter for this presentation, which is the ratio of H0 over the wavelength. And we will assume that this is small, which means that the waves are long compared to the depth. In general, we can use asymptotic methods taking into account epsilon and mu, but what I will show you today applies, we're only doing something for mu. So we can, in this literature, in this community, we usually call this type of models fully nonlinear because we leave nonlinearity as is. We don't do something for epsilon, if you want. So a state-of-the-art model is this one, which is called Serre-Green-Nagdi model, derived initially by Serre and others. Here, there are dozens of papers that derive and rederive this set of equations in different shapes and forms, equivalent to all of them. This is a model which is correct to Omicron mu, which means you have an error proportional to mu square that you neglect. It has good dispersive properties, but at sometimes it needs improvement because when you have complicated wave dynamics, you may start with a mu which is small, but during the evolution through wave-wave or wave-bottom interactions, that could change. But it has a problem. It is difficult to extend to higher orders of mu, and it was recently shown by Machuno. I will come to this back later. That when you go, for example, to mu square, like one order further, the problem is linearly ill-posed, which is very bad for both for theory and numerics, if you want. The main characteristic of another feature of this type of PDEs is that you can see that in order to involve eta and the V bar star at the next time step, you need to solve an elliptic PDE. So you need every time to compute V bar from the knowledge of V bar star and H. H here is the total depth, if you want. So at every time step, you have to solve this. Another characteristic is that, for example, if you get mu equal to 0 here, you get the nonlinear shallow water equations or the Sand-Venant equation. So this equation appear as a asymptotic correction of the nonlinear shallow water equations. So what we did here and how we can model this problem variational. The idea is to start from Luke's functional, which I write here again, impose an ansatz of this form. This is a series where Zn will be prescribed, known if you want, their form will be known. And this prescribes the vertical structure of the velocity potential, and we leave the phi n's here unknown. We put them in the functional, we vary with respect to eta and phi n with standard calculus of variation approach, and then we get the Euler-Lagrange equation, the approximating Euler-Lagrange equations, if you want. Here, I write them in a very general form, okay? We have not prescribed the vertical functions z. But they take this form. This calculation, it's not very straightforward if z depend both on eta and h, but it can be done easily if you observe that if you vary the functional s as a composite functional. I will not go into the details. The difficulty here with this approach is that we have to choose Zn. We have to choose a nice form that will give a good model, which is not a priori known. And the other thing, the good thing about that is that in our model, whatever Z we choose, that depends on eta and h, our model will have second order derivatives at most. This is good, and this is always, I say it in comparison with asymptotic models, because asymptotic models, as you raise the order, as you increase the order of approximation, you get higher and higher derivatives. And after some point, this becomes difficult to apply it numerically. So how to choose? Of course, it's not the first time that someone did that. This started late 90s, mid 90s, with the work of Isobe and Kakinuma, which is less known in the West. And they actually took an asymptotic expansion obtained from the Laplace equation and the bottom boundary condition that gives you this expression, and they used for their ansatz, for their Zns, they used this form. So even polynomials in Z that have this form. There is another approach of the group of Colloquium that is still developed, that they took a constant function and a second parabolic function, let's say. So you still have a not polynomial, but here it's difficult to extend, to go further. You can also work with an ansatz coming from the linear solution and boundary function, which is something I've worked on, extending the work of Athanasoulis and Belibasakis. But here we'll do something a little bit different that actually combines these first two approaches. We will consider the asymptotic expansion of the velocity potential obtained from the DTN problem that I showed you in the first slide. Yeah.
How do you choose the capital K? I mean, just like in your series expansion, like the ansatz.
Yeah.
You have this capital K.
Yeah, the capital K is, yeah.
So is this true that if you keep including more and more and more and more terms, you achieve
convergence?
Yeah.
You mean in the asymptotic models or the variational models?
In the previous slide, when you introduced the whole thing.
Yeah.
Yeah. That okay, you define the ansatz.
Yeah.
You say that those are the K plus 2 equations are this. So if I keep increasing the capital K, so we'll get a better and better accurate model.
I will tell you. For this approach,
yeah,
we have shown that we have convergence. Yeah, but there is a qualitative difference between this approach and this approach. This approach is constructed. I don't write here the equation because it's another, let's say it's another work a little bit different from there. But we have shown convergence and term-wise differentiability of the ansatz, and numerically we have shown convergence comparing the L2 error with exact solutions of the DTN problem. So in this kind of approaches, where your ansatz has a convergence notion there, because actually here this thing is an eigenfunction expansion, actually an improved eigenfunction expansion. So there you have a notion of convergence. Here, when you work with asymptotic expansions, convergence is a little bit more tricky. And I will not show any convergent result today, because actually We don't know even if this asymptotic expansion converges. What else I wanted to say? Yeah, and also our let's say our objective is to keep this k as small as possible. Since this k, the larger the k, the larger the elliptic PDE that you have to solve when you go in time. For example, in this approach and other approach that use Chebyshev polynomial, for example, that also converge, we know that using 5 or 7, let's say, vertical profiles can address, even the most difficult problems of non-breaking water waves. But 5 to 7 is considered a lot when you have to solve very large 2D domains. So here I'm trying to do something that it doesn't need a lot of PDEs to solve. So what we did, this expansion was initially derived by Land and Bonneton at 2009. We generalized it to higher order, and we observed that you can factorize things if you want. And phi takes this form, so it's psi. Psi depends only on x. This will give you the shallow water equations, for example. This is the next term, and you can find the vertical function z. So you have, every z is an even polynomial, and then you get higher and higher orders. So our choice is of the answers is that we take these vertical functions that we derive from an asymptotic expansion. We write them as that. We put them in the general Euler-Lagrange equations, and we finally get the system. This, for example, is for k equal to 1. I will show the general case afterwards. So you see, we have 2 evolution PDEs on eta and psi, and 1 elliptic PDE, time independent, that we have to solve during the evolution. The observation here is that this formulation is reminiscent of the Zakharov-Kreb formulation, like it is expressed on the canonical variables of the Hamiltonian system. It is also non-local, but instead of a full Laplace equation in 3D, we need to solve an elliptic PDE with variable coefficients in 2D. That saves time. Yeah.
That k was the summation, the number of terms. That means you only take the first term, right?
That means I take the constant, and one, let's say, one polynomial. Yeah. Yeah. I was talking about the Hamiltonian structure. An interesting feature of this problem, so its resemblance, if you want, with the Hamiltonian structure of the original problem. Here is the Hamiltonian, and this phi1 eta psi. Okay, we use this different notation. Actually, it's this phi. And actually, it is the operator, the solution operator, if you want, defined by eta and psi, which are the data of this problem. We have shown the Hamiltonian structure, the convergence of mass and momentum, which are classical in water waves. Water waves have more conserved quantities. We have verified these 3 for the moment. And we have shown that it's a high order approximation of the water wave equation, and they are equivalent to the Isobe-Pekinoude model obtained from the Boussinesq asymptotic expansion. I will not go into the details. I will only say that this is well studied recently by Ikushi collaborators, and its solvability in Sobolev spaces has been established. But the advantage of our approach is that the equations are derived directly in Hamiltonian form, whereas here you need a further step to formulate them as a Hamiltonian system. And if you keep them the way you derive them by the Euler-Lagrange equation, you are obligated to use an implicit scheme to solve them because they have a peculiar mathematical structure, which I will not touch today. So when you derive a model in waterways, the first thing that you want to check is its linear dispersion. So you linearize it, you assume plane wave solutions, and derive its linear dispersion. So if you take an asymptotic model using eta and psi, the blue one is the exact, let's say, dispersion relation, the dispersion relation of water waves. The black horizontal line is the dispersion relation of the Sand-Venant equations, the nonlinear shallow water, which are non-dispersive. You see that they all agree when kappa h, which is the wave number, is very small, like in very shallow.
You describe what dispersion means in this context.
Dispersion means that, okay, here C is the celerity, like the phase speed of the wave, and K is the wave number. So as the wave number changes, the phase speed of the wave changes. It's not the same. This is what we call dispersion. And the blue one is the exact, like if you take the initial equations and you linearize and calculate the dispersion, you find this curve. If you derive, for example, the shallow water equations, you will see that they are not dispersive. That is, every wave number travels with the same speed. This is true only if the water is very shallow. Very shallow means KH is very small. The black line is an asymptotic model that you get if you do asymptotics and you keep your variables eta and psi, and you see that it diverges very quickly. If you go one order further and calculate the dispersion relation, you will see that the speed of propagation becomes negative. So you have an instability. If you work with the Serre-Green-Agdi model, which is essentially these models, but you do a change of variables, and from psi you work with the depth integrated horizontal velocity. For the classical SGN model, which is the upper triangles, you get a good dispersion relation, which is quite close to the exact one. But if you go one further up, your phase speed will become infinite at a finite wave number, which is a linear ill-posedness, if you want, of the problem. In general, you don't want that. You want some linear stability because, as I said earlier, you expect during complicated wave dynamics the appearance of different wave numbers in the problem. So you don't want these wave numbers to travel, with infinite speed. It will break your simulation. This is a very recently derived model by Choi. I will not go into the details how it is derived, but it gives very close results to. It has very good dispersive properties, and the good thing is that at nu square and at nu fourth, it is linearly well posed, in contrast to the SGN model. And this is the K equal 1 model, the model I presented you earlier. And this is what you get when you use another vertical function. It's slightly better for this order in comparison with any asymptotic model that we got. And the closest you are to the linear dispersion of the original problem, the larger the domain of applicability, if you want, of the model. An additional thing that we showed is that these models, this variational model is free from a certain trough instability that was revealed recently at 2020. These authors showed that several Boussinesq type, higher order Boussinesq type model suffer from from a specific type of instability that they unveiled, assuming solution of this form and solving for the linear dispersion relation. And they got something that it was singular. And here I show you that in our case, it's non-singular. And I also have to mention that we checked that the same happens for SGN and CHOI. So both SGN and CHOI are free of this instability. But there are other Bushnell type models that are very popular and used, that they suffer from this instability, which is usually treated by smoothing or filtering. I will very quickly compare analytically with some models. Okay, this is not very important because it's not used anyway. So to gain some time, I will go to the Sergui-Nagdi model. So on the top, I write our model, and on the bottom, the SGN, which, as I said, can be considered as the state of the art here. And you see that their mathematical complexity is quite similar. Like to evolve in time, you have to solve an elliptic PDE. In this case, because you work with a velocity variable, this is a system, right? Whereas this is one PDE. So actually, in 2D, if you want, this may be slightly faster and more accurate. Yeah, and the other thing, the disadvantage, as I mentioned earlier, is that the next for practical purposes useful SGN model is the m cubed, and then you have to deal with 7th order derivatives. Whereas if you work with this, you have up to 2nd order derivatives. The comparison with the most recent high order asymptotic model is with CHOI. Here we have, again, the structure is similar. Here CHOI uses the variable f and f star, which can be understood as the trace of the velocity potential on the bottom. And because of that, the problem with CHOI is that it's not exactly Hamiltonian. So it doesn't exactly preserves the Hamiltonian, only in an asymptotical sense. And also he has a very nice proof showing that it is unstable when finite differences are used. Again, took the linear version of the problem, put the expression of the finite differences aside, and found a singular dispersion relation. So this is the general K model. We write it like that. When K increases, this is your elliptic system that you have to solve at every time step. And these are first and the third are your evolution PDEs. And the variable coefficients elliptic operator takes this form where the Greek letters are just numbers. Okay, let's go to the numerical examples. Here I will show you examples using fourth order finite differences and the Fourier pseudospectral method combined with a Runge-Kutta for explicit classical scheme. The idea is not difficult to understand. We start from we're solving the initial value problem. We start with an initial condition, and at every time step, we have to solve this elliptic PDE in order to update the right-hand side. And the only thing I have to mention, because I will show you solitary waves, because solitary waves are not periodic, the variable psi is not periodic, is anti-periodic. So when we do Fourier pseudospectral, we have to take the x derivative of this equation, or we have to double the domain in order to treat it. So the first test that we usually do in this kind of modeling is that we take an initial solitary wave and we let it propagate for a long time, and we increase its amplitude, that is, we increase the nonlinearity, and see how well our equations propagate and how stable is the solitary wave propagated through our equations. Here, because we don't yet have our proper solitary wave solutions, we use the solutions of the original problem. So here we propagate 3 solitary waves. We can say that they're exact, highly numerically accurate solutions of the initial problem. And you see that the shape and height of the solitary wave is well preserved. Here you see that behind the solitary wave, after a propagation of 150 times the depth, you have a very small dispersive trail appearing, which is expected, and actually other models, in other models, this is much more pronounced. And here I show you the conservation properties of the numerical scheme. A are the finite differences. B is the Fourier pseudospectral method that gives a very good mass conservation. But the point here is that even with a Runge-Kutta, you can have long-time simulations with very, very good preservation of the Hamiltonian. And then when you do that, you start, comparing with experiments. Usually, here is a head-on collision of solitary waves. So you start in a wave tank with 2 solitary waves. They are not exactly the same height, but they're about 0.4. 0.4 is considered highly nonlinear, a highly nonlinear case. And here we compare with the Sergri-Nagdi model, and the red line is our model. Here the circles are the experimental results, the experimental free surface elevation. And what you can see here is that here, for example, at Ts equals 0 is the moment of the maximum height during the collision. And you can also, just visually here see that the black SGN line starts losing a little bit the free surface, which means that there are high order effects that cannot be captured by an Omicron new model. You have to go higher. Yeah.
You care for energy conservation?
Yeah, here is 10 to the minus 10th.
Using RK4, and RK4 doesn't conserve energy.
Yeah. Doesn't conserve energy, but okay, it's let's say the first thing that you do. We don't want for the moment to go implicit, because we don't want add to an elliptic PDE.
No, I understand, but there are different ways to solve the problem and conserving the energy.
Not explicit.
Explicit.
Okay, I'm curious about that.
Later.
Yeah. And let me summarize a little bit. I will show you some more results. The main point is that these variational models are higher order, and you don't need more than second order derivatives. They have an exact Hamiltonian structure, which is convenient for numerics. We need the solution of elliptic PDE. We have stable solution with Fourier and finite differences. We can extend to higher order invariant bottom, and we don't have the trough instability, which is a very important feature. Now, for the variable bottom, so you go back to the DTN problem. Now you take the variable bottom into account, and you find that you have polynomials of odd degree that appear in this asymptotic expansion. So you choose your vertical functions like that, and you arrive at this problem. Similar structure, it's Hamiltonian. The Hamiltonian is positive definite as it should, and you have a system to solve because your unknowns now are phi1 and phi2. We solve this problem. This is a very classical, let's say, benchmark experiment. So you have a solitary wave soaring over a slope. The slope is 1/50, not too mild, not too steep for this context. And we also have a wall boundary condition here. This is the comparison with the experiment. Circles are the experiment, and blue is our solution. And then this set of experiments also tested the more nonlinear solitary wave. So it's a higher solitary wave. Again, it soars, it reflects, it goes back. This is the comparison with the experiment, which is very good. Another thing that we're working on is the disintegration of cosine wave. You maybe have heard it as the Zabusky-Kruskal experiment, initially solved numerically using the KDV. And we want to test this kind of model in these scenarios when you have, more complicated dynamics, more dispersive dynamics, to see how close you are to the original solution. And here you see that, okay, at least the solution is a little bit better than the SGN. Better here means that it lags less with respect to the blue curve, which is very important when you want to calculate, for example, the height in a very complicated C condition, and things that are very important for applications. And I close with some future steps that we're looking at waves of permanent form. So solitary waves have been calculated numerically for the Isobe-Kakinuma model, but the periodic nonlinear waves for this type of models are still open. We have to introduce generating and absorbing boundary condition through the use of sponge layers in order to make the problem more applicable to more realistic situations when you have incident waves that can break. The two horizontal dimensions is also a problem that we would like to go to. Here, for example, I show you a spectral solution, and here is a finite element solution. Also, in this kind of work, you also need experimental validation. There is not lack of experiments, so we have things to compare, but from what we have seen for the moment, we have a good experimental agreement to demanding cases. And another interesting extension is that because this variational principle also holds in the case of two-layer or three or multi-layer fluids separated by interfaces, you can in principle treat the problem of interfacial waves and how they interact with a free surface, which is a good approximation when you have a stratified ocean with two layers. And that's all. Thank you. Questions?
So it always probably showed us where they're, I guess, trying to find like an approximation for this height function Z. Like, how do you verify if that's actually a good approximation of the model? Is that like done analytically or?
The first verification you do is when you derive the model, you choose whatever you want. You derive your model. You linearize your model. You assume plane wave solution, that is, you say, my solution has the form of a cosine. You put this in your linearized PDE, and you arrive at a linear system that must have a non-zero determinant. And this will give you an algebraic relation that relates omega and k that are in your plane wave assumption, let's say, which is called dispersion relation. When you have that, you go and compare it with the original dispersion relation, and you hope that it will be good, that you have a close match, like I showed here. Now, here, for example, the blue one, here. Okay, let me go here. The blue one is the exact dispersion relation, is the dispersion relation that you want to, let's say, reproduce, but without solving your original problem. You derive a model, let's say the black one. You derive the dispersion relation and you compare it, and you see that they agree, but in a limited k is the wave number here. And c is omega over k, the phase speed, and you see that they agree, but near zero. The point, the objective here is to get good dispersive properties and to go, to larger k's, like you want your model as k becomes larger to agree with the blue curve. And this happens for choice model and the K1 model, for example. And as you add to your initial approximation, you expect to get better and better approximation here. But what's the thing here? Here is also, what happens linearly. Then you have to solve the problem, the full nonlinear problem, to see how good it is. And one way to see how good it is by using exact solutions of the initial problem or by experiments. I want to emphasize that because, for example, the Bushnell type models that have the Trapping stability have good linear dispersive properties. That said, this check is not enough, but it's the first that you have to do. And then you have to do numerics. You cannot do it without numerics. You cannot be sure that your model is good without numerics.
Also, you can't show, I guess all of these are expansions, right?
Yeah.
So you can't, so that they don't show analytically that it converges. Oh, I guess that's what you're talking about earlier. That you can't really.
It depends what you use. For the moment, for example, the Isobeck-Akinuma model, which is very similar and equivalent to what I've showed you today, it was recently studied mathematically, rigorously by Iguchi and collaborators. There are a series of papers. It's not easy, but they arrived to show the solvability of the problem. Now, the convergence, I think it's still open. I mean, the mathematical proof that as you increase k, you have a notion of convergence. What you can say, what you can prove, and what is actually proven is that as you increase k, you have a better and better approximation, but in an asymptotic sense. That's the thing. I mean,
you don't know how many terms are actually necessary.
Yeah. So let me close that. Like if you take the solution of the variational model and the solution of the initial problem, and you subtract them and you estimate their difference, you see that their difference is of the order of mu on 2k in the exponent 2k. This is what you will get.
So all these curves are analytical functions for the dispersion relation.
Yeah.
What about the original?
Sorry.
One? What about the original?
Yeah.
Is that also a?
It's a tan H. Where is it? Sorry. This is the original one. This is the original one.
Wait, okay, now I'm confused. Why do you need an approximation?
There is other people who want to ask.
Oh, sorry.
Because this is the linear. This is what happens in the linear problem.
Okay.
Yeah, you need an approximation because this problem is difficult to solve numerically as is, or this one. So you do approximations in order to derive models that are simpler to solve numerically.
Oh,
I was just wondering what are some applications of these models? Because I understand it's for different types of waves and things, but I guess I'm wondering what kind of scientific problems can be solved with your work?
For especially for long waves, you can study, for example, tsunami propagation. You can study waves in harbors, or how they interact with the coast, with coastal structures, like with structures that are mounted on the sea bottom. You can do landslides. For example, if you have a bottom that has a part that moves suddenly, and see what is the effect. You can do surges, that is, waves that are generated from wind in the open ocean, and then they start arriving at the coast. Stuff like that.
My understanding in wave propagation, what is numerical dispersion, is the number of grid points per wavelength that you need to resolve that.
Yeah.
That's similar to what you're saying?
No, this is physical. This is the physical dispersion. It's a property that you find in in many physical systems. This is one. This is one of them. It is a property that.
The other one is called numerical dispersion.
Yeah, the other one is called numerical dispersion. Okay, I'm sure that someone has found, and if you think about it, you will find some relation. But dispersion here appears as the property of waves of different wave number traveling at different wave speeds. This is what I tried to show with this. I cannot see here, for example, you have a high frequency wave. You have a small, you have a large wave number. It travels slower than this wave, for example. This is something that Cauchy found out and won a prize as well. But this, for example, you see at the sea that waves are not cosines, and sometimes you have waves that are not cosines. They have a persistent form. So Stokes was interested, how can this happen? I mean, if you have, for example, a wave that is not a cosine, and from Fourier analysis we know it will be a sum of cosines, how this thing will travel without changing form. And he found out that if you go to second order in nonlinearity, you see that that the wave speed also depends. When I say wave speed is equivalent to the frequency, right? Omega over k. You see that higher waves travel at different speeds. And we know in water waves and many other physical systems that when you have a nice balance between dispersion and nonlinearity, we get what we call solitary waves, that are nonlinear waves that propagate stably, and they are very persistent and difficult to destabilize in general. Yeah.
So just when you're evaluating the dispersion predicted by the linearized model, the blue curve was basically Cauchy dispersion.
Yeah. Actually, it was omega over k, because I showed you the propagation speed. Yeah, it was not omega. It was the omega over k. So it was the square root of gk tan hk.
I have one question, but okay. Maybe it's along the lines of was this person. So sometimes when you have a dispersion relation like this one or others that you can obtain analytically, and you design a numerical scheme, besides of, let's say, use a specific discretization or whatever, something that has happened in the past that it helped me figuring out what is the suitable discretization scheme was the following: that you linearize your equations, you set up the linear problem on the grid and you compute its eigenvalues.
Okay.
And then you check whether those eigenvalues line up with your explicit dispersion relation.
Okay.
So in some cases, some schemes that one can consider very highly accurate, they produce garbage.
Yeah.
If you just play around with different schemes, you start getting a better and better.
Yeah. I think actually I can say that I think what Choi did was exactly that.
Okay.
He took the linear version of his model.
Yeah.
He introduced the finite difference operators in there.
Yeah.
He derived analytically because he could the dispersion relation, and he saw that for some wave numbers, this became singular.
Okay.
But what you are saying is that you can do it. You can do that numerically. Yeah.
So that you can check and see how
Yeah.
good you can capture high wave numbers. No.
Yeah.
Okay. So.
On that note, we thank our speaker.
Thank you.
We're gonna go to have some refreshments.